A couple more examples of using half-lives and also decay modeling. We have a dose of medicine. It was injected into a patient's bloodstream, measured in milligrams per milliliter, and the half-life of the medicine is known to be 20 minutes. Find out how long it will be when the amount of medicine is 78% of the original amount. Okay, so let's go ahead and set up a model first of all for this. All right, and we know the half-life. We don't know the initial amount, but that's okay. We know that the half-life is going to be 20 minutes. So what we could do is we could use that model where 1/2 a sub 0 is going to be equal to a sub 0 e to the k times 20. And just like we've seen a few times already, the a sub zeros are going to cancel out. Okay, so whatever that initial amount is, we really don't care. And we still don't care that much throughout the entire problem. We can take the natural log of both sides. So ln of 1/2 is ln of e to the 20k. Ln's and d's are inverses. We divide by 20 to solve for k. And that's going to give us our decay constant. So ln of 1/2 over 20 is equal to k. And we can just go into our calculators. And we'll just divide that by 20. And that's going to give us negative 0.347 if we were to round it. Okay, so that's going to be negative 0.0347. Sorry, just had to check it out again. Right. And so our model is going to be that the amount is going to be equal to the initial amount, okay, which we don't know, and that's fine, e to the negative 0.0347t. And the question asks us, well, how long will it be till we have 78% of the original amount? So what we could do is we could just say, okay, well, that's going to be 0.78 of a sub naught, because that's 78% of the initial amount. Okay, so we're just going to substitute 0.78 of a sub naught back in for a, and that's going to help us to be able to figure out what the time is going to be. All right, so 0.78 a naught is going to be equal to a naught e to the negative 0.0347 t. Divide by a naught. We're going to take the natural log of both sides because ln's and e's undo each other. So we have ln of 0.78 is equal to ln of e to the negative 0.0347t. Those cancel out. We're going to divide both sides by negative 0.0347, and that's going to give us t. And so ln of 0.78 divided by negative 0.0347 is going to be equal to t. And then let's just approximate t by going in our calculators. All right, so ln of 0.78. Apparently, I don't want to type 0.78. And that's negative 0.03, I think we said 47. Yep, just to make sure. 0347. And that gives us 7.16. All right, so, and that's going to be in minutes. Okay, so that's going to be 7 point, what did we say? 16 minutes. All right. So that's not too bad, okay? And again, we keep using the same algebraic manipulatives, okay? We keep introducing a log. We cancel out the e to be able to solve these. All right, so one final question to kind of tie together exponential modeling with everything. So we have a population of deer. It was 20,000 3 years ago, and then today it is 1,400, all right? And so we're going to use an exponential model to compute the decay constant. We're going to find the population of deer after 5 years. We're going to find when the population was 300 deer, and then we're going to find the half-life. In other words, how long does it take for half of them to decay? Right. So things we know. The initial value, A naught, is 2,000. That was 3 years ago. And then after 3 years, okay, so basically that's when T is going to be 3. We have 1,400. All right, so I'm just going to say A sub naught is 2,000, and that A at 3 is 1,400. All right, and let's just substitute those back into our formula. All right, so we know that A is equal to A sub 0 e to the kt. We certainly know A naught. We're going to know A when t is 3. And so this is going to turn into 1400 is going to be equal to 2000 e to the k times 3. All right. We're going to divide both sides by our 2000. Right. So we divide by 2000, just like we've done for a lot of our exponential models. Okay. That's going to turn into 14 over 20, which if we divide both of those by 2, 7/10. All right. So this would be 7/10 equals e to the 3k. We could take the natural log of both sides. All right, so I'm just going to squeeze an ln in here. Ln's and e's cancel each other out. We can divide by 3. So ln of 7/10 over 3 is going to be equal to k. And let's just go ahead and our calculator divide that out. All right, so ln of 7 over 10 divided by 3. And that gives us 0.1189. Okay, negative. Okay, so that's going to be negative 0.1189. So that's our decay constant. And then that means that now we have our model. Our model, which we're going to call A of t, the initial amount was 2000. And we're going to have e to the negative 0.1189t. So we're going to hold on to that because that's going to help us to answer parts B, C, and D. So now we want to find the population after 5 years. All right, so that's easy. We just plug 5 in for T. So for B, we have A at 5. That's going to be 2000 e to the negative 0.1189 times 5. And that's just literally a calculator problem. All right. And so if I throw it into our calculator, we have 2000 times e to the negative, parentheses here, negative 0.1189 times 5. Let me make sure I typed all that correctly. Yep, 1189 times 5. And that gives us 1,103. We know that we can't have 0.67 deer, okay? So we'll just round it down to 1103. Okay, so that's going to be our population after 5 years should be 1103. Just making sure. All right. Now, our third part asks us find when the population will be 300. Okay, so that should be a number of years down the road. If after 5 years it was 1100, it's certainly going to be more than 5 years. Okay, so we're going to plug in 300. So we have 300 is going to be equal to 2000 e to the negative 0.1189 t. Right? We divide by 2000. When we cancel things out, that's going to leave us 3/20ths. Okay, so we have 3 over 20 is going to be equal to e to the negative 0.1189t. Let's take the natural log of both sides. All right, ln's and e's cancel each other out. So, and we would divide by negative 0.1189 to solve for t. So the natural log of 3/20ths over negative 0.1189 is going to be equal to t. And let's just approximate that. So in our calculator, we have natural log of 3 over 20. And we are going to divide that by negative 0.1189. So about 15.96 years. Okay, so about 15.9, what do we say? 956 years. All right. So it's a pretty good amount of time until our deer population reaches that 300. All right. Now, we've seen that there's about 1103 deer in year 5. Okay, so the last part of it asks us for the half-life, and half of 2000 is going to be 1,000. All right, so to me, it seems like it should be pretty close or somewhere in the neighborhood of 5. Right, so if the half-life is 1,000, okay, or I'm sorry, the half amount is 1,000, we want to find the half-life, all we're going to do is just substitute 1,000 back in for A and then solve, right? So for letter D, we're going to substitute 1,000 is equal to 2,000 e to the negative 0.1189 t. All right. So, and again, we're trying to solve for the half-life. So basically, what year does t give us half the initial amount? So we're going to divide by 2,000. So if we divide by 2,000, that's just going to leave us with a half, which is expected since we're trying to find the half-life. That's going to be e to the negative 0.1189t. We take the natural log of both sides. ln's and d's cancel each other out. We're going to divide by negative 0.1189. Negative, all right? And that should give us our t, right? So t is going to be approximately 1/2. I'll just change this to 1/2. And 5.8296, so 5.83 years. Okay, so t is going to be 5.83 years. Okay, is the half-life of the deer, which makes sense because remember, in part B, it took 5 years to give us 1103. So a little bit more than 5 years, 5.83 years. That makes sense that that's going to be the half-life. All right, so that's all we're going to do with our exponential decay and growth for now, but we still have to go through the logistic equation and Newton's law of cooling, which we'll do in our next videos.